Hey everyone, welcome back to our scenes. So in today's video, we are going to talk about Ohm's law. And as you can see here, it is on page number 98 of your part 1 book. So here you have got this blue color box, which consists of a diagram. Okay, and you have got a tabular column over here. Okay, so we are supposed to be conducting an experiment over here. Okay, this is the circuit diagram. We have to arrange everything in this manner and then fill the tabular columns below. So we're going to talk about it one by one now. So as you can see here, for your diagram, circuit diagram, we have got 4 cells with a dotted line over here. Okay, so this depending upon the 4 trials, for the first trial, second trial, third and fourth. Then we have got a switch, an ammeter over here. We have got resistor. Okay, what is this resistor? I'll be telling you later on. Okay, and then across this resistor, we have got a voltmeter connected. As if you can remember, I have already told you, voltmeter is always connected in parallel combination, whereas ammeter in series combination. Now let's see what do we have in the tabular column. We have got serial number. We have got number of cells used in the circuit, which is already given here, 1, 2, 3, 4, already printed out. Then next thing comes the current, okay, going through the nichrome wire. The wire used here is nichrome wire, I. Okay, so the readings in the ammeter, that is what we are supposed to note down over here, which I have already done over here, so that it becomes easier, to go on with the explanation. Then comes the potential difference across the nichrome wire, V, volt. So that is supposed to be this reading. Okay, so for each trial, I'm going to calculate, I'm going to write down the V of value of will be of this. So what value I get over here, that is supposed to be noted down here for each trial. And lastly, V upon I, I'm going to divide my V value with the I value for each trial, and I'm going to see what values I get. Okay, so let's get started now. So let's start with the first trial. For the first trial, I'm going to use only one cell. Okay, so this is going to be the connection for this, for the first trial circuit. So rest all is going to be the same. I'll say here, since the dot is present, the switch is off. I'm going to switch it on, and I'm going to let the current pass through it. So as I let the current pass through it, what happens is I will be getting a reading in the ammeter and voltmeter, right? So I'm going to note it down. The reading in the ammeter will come over here. I have already noted it down. So in the first case, it's 1. And in the second case, in the voltmeter case, it's going to be 5. This will be dealing with later on. Okay. So now, going on with the second trial. So for the second trial, I'll be adding up 2 cells. Okay, so this line is not valid. We are going to show a connection over here. So this is not the connection. So 2 cells together and this connection. Okay, we'll let the current pass. We'll switch it on. And again, as the current is passing, okay, I'll get a reading over here of 2 ampere. And in the voltmeter, I'll be getting 10 volts. Okay, so I have got a reading over here again. Now, for the third trial, I'll be taking 3 cells. Again, the same procedure. Okay, I'll be getting a value which I'll be noting down. Okay, so in this case, it's going to be 3 amperes with 15 volts. Lastly, for the last trial, 4 cells together connected. And I'll be letting the current pass through it. I'll be getting a reading in the ammeter and the voltmeter, which is supposed to be 4 amperes for the ammeter and 20 volts for the voltmeter. Now what I'm going to do is, for the last column, V upon I. So for each trial, I'm going to divide V by I. So in the first case, 5 upon 1 is 5. 10 upon 2 is going to be 5. 15 upon 3 is going to be 5. And 24 upon 4 is also 5. So the thing which we have noted down here is, in each case, if I would have gone further on with the trial, if I divide V upon I, I'm going to get the same value. So it's constant, right? So we are getting this constant value, and this is very, very much needed. if you don't get a constant value, it's going to be difficult. It won't justify your Ohm's law. So Ohm's law is based on the justification of the constant value of V upon I. So this constant value which we get, we call it as R, resistance. So this is what is resistance. This is a constant value which you get on dividing V with I. Okay, so now let's see below how do you define this Ohm's law. So you have got this. I will be showing you how your definition is in your textbook itself so that it becomes easier when you're referring your textbook. So it starts somewhere here and it ends over here. The entire thing you're supposed to write. So whenever you're writing a physics law, remember that you have got mathematical equations for it and you are supposed to definitely write it even if asked or not. Definitely they'll be asking you the mathematical equations for physics laws. It's 100% guarantee. Okay, so now. So what you're supposed to do is, before seeing the definition, you're going to see the graph. If you plot the graph, for whatever readings you are getting, here they have shown a different reading. Okay, so it's not needed that whatever readings I have got, you are supposed to get the same. The readings might differ, but always remember that this constant value, okay, not only 5, whatever you get, okay, suppose if you, in your case, if you are getting 0.3, so it's supposed to be the same throughout for every trial for the same setup. So that is what is needed, a constant value. These readings might differ from person to person, okay, depending upon your equipments, whatever you are using, depending upon the type of wire and everything. But the constant value has to be maintained. So now, on plotting a graph, okay, on your y-axis, if you plot potential difference, that is V, and on your x-axis, if you are plotting current, that is A, and if you start plotting whatever trial values if you get, you are going to get a line, a straight line passing through the origin, that is O. Okay, so this is what actually justifies your Ohm's law. So as potential difference increases, what you observe is your current is also increasing equally. That is the reason why you get a graph exactly passing through the origin. So now if you have to define, which is the very main point for your board exam, okay, you are supposed to define is as follows. The potential difference V across the ends of a given metallic wire in an electric circuit, we are talking about this bolt, okay, across the metallic wire of 2 ends, is directly proportional to the current flowing through it. Directly proportional. What is this directly proportional? I'll be telling you. But what is the condition over here? Provided its temperature remains the same. So voltage is directly proportional to the current only and only if your temperature is constant. Your temperature is not changing around you. So this is what we call as Ohm's law. So if I have to write down mathematically, they have told me that voltage is directly proportional to current. Voltage is denoted as V and current is denoted as I. This is the symbol for proportionality. Both are directly proportional, hence both are in the numerator zone. Okay, this shows that when V increases, I increase. If V decrease, I decrease. That means, whatever happens to V, in the same manner, I will be affected. So, now, if you remove this proportionality symbol, if you write this as is equal to, if you bring this I in the denominator of V, something like this, V upon I, you are going to get a constant value, what we have observed over here. This constant value is called R. This is not specific for each and every experiment, but for each and every setup, this value is going to be the same. So in short, if V upon I is equal to R, then this I, if it comes over here, V is going to be IR. And this is the final statement, what we are using for your experiment, problem purpose and all. Now let's talk about this R. Okay, how do you define this R and how this R works out? So as I told you before, R is nothing but resistance. So how do you define this resistance now? Okay, so in short, if I have to define resistance, it is nothing but hindrance in the flow of current. Imagine you have got a wire, okay, and suppose this is a section of a wire and the current is flowing through it. Okay, so it's not just a simple pipe so that the current can easily, it's not like water is completely flowing through it. You have got electrons over here and these electrons are attracted towards one another. Okay, there is a force of attraction existing between them. So hence, whenever the current is trying to flow through it, it's like you're going through a sea of electrons. Okay, so like we are passing through a crowd. It actually slows down our speed. Same thing, because of the attraction between these electrons, the flow of current is being, the flow of current is not always so smooth. They have to fight their way through all these attracted electrons and they have to reach the other end. So in some conductors, depending upon the type of material, this attraction is less. In some, it is very high. So if the attraction is very high, or if at all this hindrance is very high, then resistance is high. If the resistance is low, then the current can flow easily. If the resistance is high, then that means the problem or the difficulties are very high. The hurdles are too much and the current is not able to flow easily. Okay, so normally when do you call a conductor as a good conductor? When it offers low resistance. If resistance is low, current will move easily and there will not be wastage of current. So if resistance is high, because of the difficulty in passing, most of the current is lost in the form of heat. Like for example, we use electric iron, right? So electric iron offers very high resistance. That is the reason why your electric iron gets heated fast. So heating appliances actually use very high current. They actually produce very high resistance. Okay, so that's about resistance. Now let's talk about resistors, what we have been seeing over here. Okay, the zigzag patterns what we have been seeing here, these are nothing but resistors. So these resistors are nothing but a small equipment kind of thing which will have on it, suppose if I'm showing you a resistor and on it it's written 5 ohms. Ohm is nothing but its unit. The unit of resistors is ohm. Okay, resistance, and it is denoted as this is omega. Okay, as you can see here, okay, this is omega, symbol for ohm. Okay, so now when you're talking about resistors, it's actually nothing but a small equipment with a fixed resistance. So if you are connecting that particular resistor, suppose if I have chosen here a 5 ohm resistance, then the resistance offered throughout by this will be only 5 ohms. So this is a fixed value which is normally used for different experiments, not only Ohm's law. Then comes another one, that is rheostat, which also we have discussed here, in your in your circuit symbol which I have told you before. Okay, rheostat is actually what should I say, an equipment where your resistance is not fixed. You can change the resistance, you can tune it depending upon your need. So that kind of resistance or resistor, we call it as rheostat. As you can see here on the screen. Okay, so now let's try and decide, okay, how do you define resistance, okay, or how do you define 1 ohm. So as you know, V upon I is equal to R. This is according to your Ohm's law, right? So we know that the unit of resistance is ohm. So if I just substitute this with the values of its SI unit, resistance is 1 ohm, volt is 1 volt, potential difference, and electric current is 1 ampere. So 1 ohm resistance can be defined as okay, across the two ends, it can be defined as 1 volt of potential difference with 1 ampere current. Okay, so that is how you're supposed to define it. Okay, so that's about it now. In my next class, we'll be dealing with the rest of the parts. If you have any doubt regarding Ohm's law, you can just leave a comment in the comment section and I'll get back to you as soon as possible. Thank you for watching.